As far as Joule-Kelvin effect is concerned, when a gas at high constant pressure is passed through an insulated porous plug to a region of lower pressure, a change in temperature is taken place. The change in temperature is proportional to the difference in pressure on both sides of the plug. This is the expression for cooling. dt equal to P1 minus P2 by Cp into 2A by RT minus P. Here P1 minus P2 is our change in pressure, that is dP. C suffix P is the specific capacity at constant pressure. For the given temperature, the quantity P1 minus P2 is always positive, whereas the value of 2A by RT minus B determines the nature of the effect. Suppose 2A by RT minus B is positive, the quantity 2A by RT is greater than B, or T is less than 2A by RB. Under this condition, the value of dt is positive, then cooling will be taken place since T1 is greater than T2. If 2A by RT minus B is negative, 2A by RT is less than B, or T is greater than 2A by RB. Now heating effect is taken place because the value of dt will be negative, then T1 is less than T2. If 2A by RT minus B is 0, 2A by RT equal to B, then T equal to 2A by RB, then dt equal to 0. Then there is no change in the temperature of the gas. This temperature is known as temperature of inversion, Ta equal to 2A by RB. The temperature at which Joule-Thomson effect is 0. Here Joule-Kelvin effect is also called as Joule-Thomson effect. It's known as temperature of inversion. All the gases above the temperature of inversion would show a heating effect. For hydrogen, the temperature of inversion value is minus 80 degrees Celsius, whereas it is minus 240 degrees Celsius for helium. Hydrogen and helium show heating effect at ordinary temperatures. This is a relation between critical temperature and the temperature of inversion. The value of Tc is 80 divided by 27 Rb, whereas Ta is 2A by Rb. Then the value of Ti by Tc is 27 by 4, which is equal to 6.75. Hence, the ratio of temperature of inversion and critical temperature is constant and is independent of the nature of the gas. In Joule-Kelvin effect, enthalpy of the gas remains constant. So it is a isoenthalpic expansion process. You know that the heat content of a system at constant pressure is called enthalpy. Enthalpy is given by the formula H equal to U plus PV. If you go for the liquefaction of gases, gases at ordinary temperatures could be converted into liquid if sufficiently cooled and sufficiently subjected to a high pressure. Faraday in 1825 attempted to liquefy certain gases and succeeded in his attempt to liquefy ammonia, chlorine, carbon dioxide and sulfur dioxide. But attempts to liquefy O2, N2 and H2 failed, and thus these gases were called permanent gases. Liquefaction of oxygen. Critical temperature of oxygen is minus 118 degrees Celsius. Oxygen therefore must be cooled to a temperature below this critical temperature for liquefaction. What would be the pressure you may apply? If the temperature is greater than the critical temperature, no liquefaction is taken place. K1 is the liquefied oxygen. As far as the liquefaction of air is concerned, Lind and Thomson in 1895 used Joule-Kelvin effect and the principle of refrigerative cooling in liquefaction of air. Hydrogen at ordinary temperatures shows a heating effect on thermal expansion. Temperature of inversion of hydrogen is minus 80 degrees Celsius, but for practical purpose, a temperature below minus 170 degrees Celsius is essential to get appreciable cooling. Such a low temperature is attained by immersing the apparatus in a liquid air. Liquid hydrogen boils at minus 252.78 degrees Celsius under atmospheric pressure. Temperature of inversion of helium is 35 Kelvin, but practical purpose the gas is cooled to 17 Kelvin. It was K1 who was able to liquefy helium in 1908 by the presence of regenerative cooling. Liquid helium above a temperature of 2.19 K is called helium 1. Helium 1 behaves in a normal way. Liquid helium below 2.19 K is called helium 2. Helium 2 has abnormal properties. Specific heat of liquid helium increases up to 2.19 K, and at this temperature there is a sudden and abnormal increase in specific heat. See here, if you increase the temperature, the specific capacity increases gradually, but at 2.19 K it increases abruptly and then decreases. So this curve is identical with the symbol of lambda. Therefore, this point 2.19 K is called the lambda point. The very high specific heat of liquid helium at lambda point is due to rapid decrease in its entropy. This is a complicated phenomena and can be explained on the basis of Bose-Einstein statistics. Viscosity of helium 2 decreases with the decrease in temperature, but viscosity of helium 2 is practically zero. Viscosity of helium 1 decreases with the decrease in temperature. However, the viscosity of helium 2 is zero practically. Helium 2 can flow rapidly even through an extremely narrow capillary tube. Helium 2 forms a film on a solid surfaces. Such a film is called as rolling film. Thermal conductivity of helium 2 is very high. Thermal conductivity of helium 2 is many times higher than that of copper and silver. Helium 2 has a higher heat of vaporization and a smaller surface tension. Then the thermal conductivity. The coefficient of thermal conductivity is defined as the amount of heat flowing in 1 second across the opposite face of a cube of side of unit length of maintained at difference of 1 degree Celsius. Q is proportional to area of cross section, proportional to difference of temperature, directly proportional to time, and inversely proportional to distance. If you compile all these things, you can get this equation. To remove the proportional design, we have introduced a constant K. If area of cross section is 1 centimeter square, temperature difference is 1 degree Celsius, time is 1 second, x is 1 centimeter, then Q equal to K. Here theta 1 minus theta 2 by x is called temperature gradient. It's a negative quantity. As temperature decreases, the increase in distance from the hot end, the quantity d theta by dx is negative. Therefore, Q equal to minus K into d theta by dx into T. K equal to Q divided by A into d theta by dx into T. Unit of thermal conductivity is watt meter per minus 1, Kelvin per minus 1. Then this is the dimensional formula for thermal conductivity. To determine thermal conductivity, we are suggesting forced method. Here we are following two methods. One is static part and another one is dynamic part. This is the formula for thermal conductivity. As far as the forced method is concerned, in the static experiment, a graph is drawn by taking distance along the x-axis and temperature along the y-axis. From the graph, we have arrived to the value of d theta by dx, which is equal to tan alpha. Then from the dynamic part, a graph is drawn between temperature and time. For various values of theta, d theta by dt is determined. With the help of the two graphs, a third graph is drawn. With the help of the third graph, arrived to the value of d theta by dt dx, which is nothing but the area of the shaded portion. Then the drawbacks existing in the forced method include: it takes long time and three graphs are to be drawn. Distribution of heat is not uniform. Specific heat is not constant at all temperatures. But the major advantage is absolute conductivity of the material can be determined. With the help of the least disk method, we can determine the thermal conductivity of the bad conductors like rubber, glass, ebonite, wood, cork, etc. In the Stephen's law, the rate of emission of radiation from a perfect black body is directly proportional to fourth power of the absolute temperature. To remove the proportional design, we are using a constant sigma, which is called as Stephen's constant. If the body is not a perfect black body, we have to add one term E, emissivity power. For a perfect black body, the emissivity power is 1. If it is not a perfect black body, the emissivity power varies between 0 and 1. This law holds good for absorption and emission. When the temperature of the body is equal to the temperature of the surroundings, the rate of emission and absorption are equal. R is proportional to T1 power 4 minus T2 power 4. Then R equal to sigma into T1 power 4 minus T2 power 4. If it is not a perfect black body, we have to include the emissivity power. Then we may get the Newton's law of cooling from this. Suppose the temperature difference is very small, we may get our Newton's law. When the temperature difference is small, Stephen's law is reduced into Newton's law of cooling. Here the value of Stephen's constant is expressed in terms of CGS, that is 5.672 into 10 power minus 5, and the sigma equal to 5.67 to 10 power minus 8. The unit is watt per meter square, Kelvin power 4. And this is the definition for solar constant. It is the amount of heat energy absorbed per minute by 1 square centimeter of a perfect black body surface placed at a mean distance of the Earth from the Sun in the absence of the atmosphere, the surface being held perpendicular to the Sun's rays. Then the temperature of the Sun is 5730 Kelvin, which is almost 6000 Kelvin. With the help of Wien's displacement law, the Wien's displacement law is lambda m is inversely proportional to T. Then we may estimate the temperature of the Sun as 5987 Kelvin. The radius of the Sun is 7 into 10 power 10 centimeter or 7 into 10 power 8 meter. Then we will go to thermodynamics, which talks the relation between heat and mechanical work. Usually, the work can be completely converted into heat energy, but the converse is not to. We won't convert the total heat energy into mechanical work. W is proportional to H. W equal to J into H. The value of J is 4.186 joule per calorie or 4.186 into 10 power 7 X per calorie. Zeroth law. Suppose three systems A, B and C are taken for consideration. The system A is in thermal equilibrium with B and C separately, then they are in equilibrium with each other. The consequence of zeroth law is temperature. Then the first law is concerned. The quantity of heat energy given to the system is utilized in two ways. Part of the energy is used to increase the internal energy of the system, and the rest is utilized to carry out some external work done. If you replace del W by PdV, this is called a differential form. First law in terms of entropy is TdS equal to du plus PdV, because the change in entropy ds equal to del Q by T. So del Q is equal to T into ds. The consequence of first law of thermodynamics is internal energy. The physical significance and limitations of the first law. The first law is simply the conservation of energy principle in its most general form. It recognizes the transfer of energy through either work or heat. It doesn't specify the condition at which a body can use its heat energy to produce work. It does not say how much heat energy is converted into mechanical work. In thermodynamics, the state of a macro system is defined in terms of a few experimentally observed parameters known as thermodynamic variable. Volume, temperature and pressure are thermodynamic variables. These are all called state variables. What is meant by internal energy? The sum of kinetic and potential energies of all the gas molecules taken together is known as internal energy of the gas. But in general, we may point out heat content of the system at constant volume is called internal energy, whereas the heat content of the system at constant pressure is called our enthalpy. Isobaric process. In this process, pressure remains constant. In the PV diagram, if you see the pressure curve, which is parallel to the volume axis. For an isobaric process, this is the first law. Isochoric process is a process in which volume remains constant. See, this is isochoric process. Here the curve is a straight line parallel to the pressure axis. In an isothermal process, the change in internal energy is zero. See here, in our isochoric process, volume remains constant, so del Q equal to del U. Because from the first law, del Q equal to du plus PdV. If it is isochoric, this factor is 0. So del Q equal to du. The given heat energy is totally converted into internal energy. Isothermal process. In this process, temperature remains constant. When a change in pressure and volume of a substance takes place, but the temperature remains constant, the process is said to be isothermal. In an isothermal process, the change in internal energy is 0. Therefore, del Q equal to du plus del W. This is the first law. If d equal to 0, del Q equal to del W. In an isothermal process, heat added or subtracted is equal to external work done by or on the gas. If it is isothermal expansion, work is done by the working substance. If it is isothermal compression, work is done on the substance. For a perfect gas, an isothermal change is represented by Boyle's law, that is PV equal to constant. Isothermal process is a slow process. The walls are conducting in nature. These are all the examples. Phase transformation, that is solid to liquid, liquid to gas, refrigerator and heat pump. Adiabatic process, when a change in pressure and volume of a substance takes place but no heat is allowed to enter or leave, the change is said to be adiabatic. During an adiabatic process, del Q equal to 0, therefore du equal to minus del W. In an adiabatic process, increase or decrease in internal energy is equal to external work done on or by the gas. With respect to expansion or compression, this is justified. The equation is PV power gamma is a constant. In an adiabatic process, entropy is a constant, whereas in an isothermal process, temperature remains constant. Adiabatic process is a quick process. The walls are non-conducting in nature. If you see the slope of an adiabatic, that is gamma times the slope of an isothermal. Already we talked about the same. Isothermal process is a slow process, whereas the adiabatic process is a quick process, so it has higher slope. For an isothermal process, PV is equal to constant, whereas for an adiabatic, PV power gamma is a constant. From this, find out dP by dV. Using this equation, find out dP by dV. If you compare these two things, you can get this result. Slope of an adiabatic is gamma times slope of an isothermal. The same logic is true for elastic property also. E adiabatic equal to gamma times E isothermal. These are examples of adiabatic process. A pendulum oscillating in a vertical plane, a quantum harmonic oscillator, ice in an ice box. If you think about an ice in an ice box, neither heat energy is given or taken from the box. Release of air from a pneumatic tire. Work done in an isothermal process using the formula PdV. If you make your integration, you can get this result. For n moles, W equal to nRT into log to the base E, V2 by V1. If you want to convert this in terms of base 10, it should be multiplied by 2.303. This is a formula for work done in an isothermal adiabatic process. Say, just integrate and you can get this result. P1 V1 equal to RT1, P2 equal to RT2, then W equal to 1 divided by gamma minus 1 into RT1 minus RT2. Take the R outside, this is the final result. If there is an adiabatic compression, the temperature of the gas will increase. If there is an adiabatic expansion, the temperature of the gas will decrease. Cyclic process. In the cyclic process, the system after passing from initial state to final state comes back to its initial state. In this process, the net change in internal energy of the system is 0. That means del Q equal to del W. In the cyclic process, the heat taken by the system is equal to work done by the system. In differential form, integral del Q is closed integral equal to del W. Reversal process. A reversal process is one that can be reversed in such a way that all the changes taking place in the direct process are exactly repeated in reverse order. All isothermal and adiabatic processes are reversible when performed slowly. The necessary condition for a reversal process, all dissipative forces such as friction, viscosity, etc., must be exactly absent. The process must be quasi-static. These conditions are never realized in practice. Hence, a reversal process is only an ideal one. Example of reversal process: ice to water, then water to ice. If the resistance of a thermocouple is neglected, there will be no heat produced due to Joule heating effect. In such a case, Peltier heating or cooling is reversible. Electrolysis is another one example. Irreversible process. An irreversible process is one that cannot be retraced in the opposite direction. Work done against friction is irreversible. The Joule-Kelvin effect is irreversible. On reversing the flow of gas, similar cooling or heating effect is not observed. Similarly, diffusion, conduction, and radiation are irreversible. Then the heat engines. The heat generated when a current flows through an resistance is also irreversible. The rusting of ion is an example of an irreversible process. Then if you go to second law of thermodynamics, this is our Kelvin statement. It is impossible to get continuous supply of heat energy from a body by cooling it to a temperature lower than the coldest of its surroundings. This is our Clausius statement. It's impossible for a self-acting machine unaided by any external agency to convert heat from a body at a lower temperature to a body at a higher temperature. In actual practice, the efficiency of heat engine is very small and ranges between 5 to 25%, which means that only 5 to 25% of heat energy is converted into mechanical work. Carnot designed an ideal engine. It consists of a source, sink, non-conducting stand, and a working substance. We can draw any amount of heat energy from the source, which is maintained at a temperature of T1 Kelvin. We may provide any amount of heat energy to a sink, which is maintained at a temperature of T2 Kelvin. Non-conducting stand and working substances are the two other compartments. Here the efficiency of the Carnot engine is 1 minus T2 by T1. We cannot harvest 100% efficiency since the temperature of the sink not equal to 0 Kelvin. It is at an arbitrary temperature. Carnot cycle contains 4 operations: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Just we have given the operations and the corresponding equations one by one. Just go through the same. From this we may find the work done Q1 minus Q2 using this formula. R into T1 minus T2 log V2 by V1. This is the value of Q1. If you put up, you may get the efficiency equation eta. Carnot cycle is perfectly reversible. It can work as a heat engine and also refrigerator. Then the coefficient of performance is given by the formula beta equal to T2 by T1 minus T2. The coefficient of performance of a refrigerator is defined as the rate of change of the heat drawn from the cold body to the work done on the machine. This is the formula for entropy. Entropy measures disorder of the system. The change in entropy equal to del Q by T. Entropy is also a state variable. In a reversible process, entropy is constant. So the change in entropy is 0, which means that S equal to constant. In an irreversible process, entropy always increases. All the natural processes are irreversible. Therefore, the entropy increases. The entropy of the universe always increases, which is leading to the concept of heat death or thermal death. This is Clausius inequality. Delta S, change in entropy, is greater than or equal to 0. If the process is reversible, delta S equal to 0, therefore S equal to constant. If the process is irreversible, delta S is greater than 0, which means that the entropy increases. Law of increase of entropy. The tendency of an isolated system to shift towards a state of higher entropy in irreversible process is called the law of increase of entropy. This is our Carnot theorem. All reversible heat engines working between the same two temperature limits have the same efficiency, which is our Carnot theorem. Isentropic process, entropy remains constant. A gas undergoing an adiabatic change is an example of an isentropic process. Then the Maxwell's thermodynamic relations. This is the first relation, dou S by dou V at constant T equal to dou P by dou T at constant V. See here we are following a technique to get these equations. SPTV, SP, Superintendent of Police, television. SPTV, if you follow this cycle, all are positive. If the volume is changing, temperature constant. Here the temperature is changing, volume constant. You know that change in entropy equal to dou Q by T or dou H by T. So that this equation is modified, dou Q by dou V at constant T equal to T into dou P by dou T at constant V. Then if you go to the second equation, see here we are operating clockwise operation SPTV. Here in anti-clockwise we are writing SPTV so that we have introduced a negative sign. Then dou S should be replaced by dou Q by dou T. You can get this equation. Then in this equation we are starting our process from the bottom, SPTV. So we have introduced a negative sign. In the next equation, we are operating from the bottom in the anti-clockwise direction. If you take the bottom, this is in anti-clockwise, so negative sign. If you think about this equation, here also we are starting our journey from the bottom, so that this is in clockwise, so we are using positive sign. See the first equation, SPTV in this order, so all are positive. In the next equation, we are maintaining the anti-clockwise operation. See, this is first equation, SPTV, so that we are using positive. Here we are using anti-clockwise direction, so we have given negative. Then in the third equation, we are starting our journey from the denominator, SPTV in the anti-clockwise direction, so we have given negative sign. The next equation, we have given SPTV in clockwise direction, so it is positive. See this equation, temperature versus entropy. Temperature, entropy, pressure, volume, minus. Then just change the volume and the pressure, dou T by dou V, dou S by dou P, which is equal to 1. This is pressure versus volume. PV is a variables present in the numerator, TS. Just if you interchange, you may get the second term, which is equal to 1. Then the third law of thermodynamics. Third law is based on the unattainability of absolute zero. For any system, even an ideal case, it is impossible by any procedure to reduce its temperature to absolute zero in a finite number of operations. But we know that at absolute zero, entropy approaches zero. But absolute zero is not possible. This is our third law. Once again, I am repeating the Maxwell's relation. See, in this relation, we are using SPTV in the cyclic process, so all are positive. Then dou S is replaced by the formula, dou S equal to dou Q by dou T or dou H by T. This is also correct. Dou S equal to dou H by T. So instead of dou S, we may put dou Q by T. See this relation. Dou Q by dou V at constant T equal to T into dou P by dou T. The second relation, we are keeping the things in the anti-clockwise direction, SPTV. So we have introduced a negative sign. Then in this equation, from the bottom itself, we are starting our journey. SPTV in the anti-clockwise direction. So we have introduced a negative sign. But in this equation, we are operating in the clockwise direction from the bottom, SPTV. So all are positive. In the last two equations, temperature versus entropy, TS, here PV. Just we have interchanged dou T by dou P at constant V, dou S by dou V at constant P. Here dou T by dou V at constant P, dou S by dou P at constant V equal to 1. Here pressure, volume are the variables, pressure, volume. Automatically temperature and entropy are coming to the denominator. So in this way, we can sketch out these Maxwell's thermodynamic relations. So that in the next video, we will give and discuss all the objective questions existing in this unit.